Welcome back. So today we are going, or this video, the second part of this video, we're just going to talk about binding energy. I realize that 2 slides down is just going to be the next lesson. So, so maybe, well, actually about 3 slides down. I could have just tacked this onto the last one. So this would be a nice little short one. So this diagram here just talks about the binding energy per nucleon. So these numbers are just taking the binding energy that we found, so this number that up here, and then dividing it by how many nucleons there are, right, in that very particular isotope. So in this case, if I wanted to go for this one, I would divide this by 12. So 89.3 divided by 12, and you get a binding energy of about 7.44. Okay, so you can look down here in this chart. 7.44 would be in this little range right over here. Because my atomic mass number would be 12, I would be pretty close right about here. So oxygen has a little spike and then it goes back down. So all these numbers here on this chart are taking these mass defects that you found here and dividing it by how many nucleons they are. And you can see a weird little trend. So it starts off really low. Right? So hydrogen 2, there's an isotope of hydrogen. Usually hydrogen is hydrogen 1. So this one has a proton and a neutron in it. Has a really low number, right? And then it kind of spikes up, goes up a little bit. There's a little trend. It kind of goes up and down a little bit here too. You're not seeing all the elements. You're only seeing some of the more common ones. But you can see the trend goes up, goes up, goes up, and then it peaks. And this is where it peaks. It peaks at iron 56. So this is right at the peak. I don't know the exact number there, as we can find out what that number is if you wanted to. I have a whole chart of atomic mass units, but that is the top of this chart, and everything after that gets, the more massive it is, the less energy per nucleon there is. Now this tells us a lot of things about fusion and fission when we get into those kind of things next week when we talk about fusion and fission. Now, what this is saying is that because that is the most energy per nucleon, iron is technically the most stable. Iron 56 is the most stable of all the elements. Now, it doesn't mean that on either side of this, like hydrogen 2 is very unstable. It's not unstable. Like those are pretty stable elements. Helium 3 is a pretty stable element. Helium 4 is pretty stable. Right? Oxygen 16 is pretty stable. All these elements are pretty stable. You do get more radioactive as you go down to the uranium, but that's only because there's so many protons in it that it wants to separate. It wants to split up and cause what we call fission, when something big separates into something small. But the cool thing about this is that if you're on the left side, so if you're over here, if you're on this side of the chart, if you were to fuse 2 things together, fusing means just taking, we'll talk about this later too, taking 2 smaller elements and then fusing them together, right? If you say take 2 hydrogens, these guys, and then add 2 of them together, and I fuse them together, I'm going to get helium. And by doing that fusion, it's going to release energy, which is a fun little thing, right? So on this side here, fusion releases energy. So I'm taking 2 smaller things and I fuse them together, it's going to release energy. Okay? And if I'm on the other side over here, this side over here says fission releases energy. Now fission is the exact opposite. It takes something larger. If you take something larger, it becomes 2 smaller elements. That's fission, and that's going to release energy. Now, it's also saying that if you're on that side, if fission releases energy, then on that side, fusion would absorb energy. This is where it becomes to more the nature of our sun and planets or suns that die off. Because what's inside the sun right now is a bunch of hydrogen and helium, and they're all fusing together. As you run out of hydrogen, the helium starts fusing together. As those run out of heliums, say oxygen starts fusing together, or whatever, what's for beryllium starts fusing together. Those berylliums fuse together to create oxygen. Those oxygens fuse together to create sulfur. Those sulfurs fuse together to produce whatever 32 is, uranium, and a bunch of other ones too, because they don't have to fuse with each other. They can fuse with whatever's sitting around. And eventually what we're going to get to something that's too large. They're going to create these larger elements. They're going to create iron. They're going to create cobalt, nickel. Actually, uranium is actually too large at this point, right? So once you get past a certain point, you're creating too much. And if you run out of the smaller stuff, then the sun is start going to fuse those together. And you're going to fuse iron together with itself, or fuse tin together with something else, or uranium with something else. By fusing them together that way, it's start going to absorb energy rather than release energy. So all up to that point, all these fusions of smaller things is releasing energy. That's fine and dandy. The sun is producing heavier and heavier elements by doing so. By the time it's going to hit this tipping point, once you get past iron and you run out of the smaller stuff, the iron, the bigger stuff is going to start fusing together. And by doing so, you're going to absorb energy, and the sun is going to start dying off. Rather than releasing energy, it's going to take in the energy that it was releasing before and start cooling down, and then become two situations there. Become too heavy too fast, it becomes a black hole. It's supernovas, it just goes crazy and just explodes. Or it just grows in size because it no longer can hold itself together and just gets bigger and bigger and becomes what we call a red giant. Anyway, that's beside the point. Yeah, I just want to make this video longer because a little video. What do we have? 6 minutes. Okay. So many of these isotopes up here, right? They are proven to exist, right? Very few of them are actually considered stable and non-radioactive. So this little chart down here, if you look at this chart, all these little black dots here, in the bottom here would be your atomic number. The side here would be your neutrons, right? This line down here, so this is protons on the bottom and neutrons on the side. The line down the middle is where you would have equal number of protons and equal number of neutrons. So it starts off pretty nice. Let's see here, until you get to around 20, which is calcium, where stable elements have the same number of protons, the same number of neutrons. Now the neutrons are in there to give the protons space. If the protons are too close, the force is too big. So the neutrons kind of space them out a little bit nicer so that they're not so close together. So the electrostatic force is a bit weaker. So the strong nuclear force works. But once you start getting too many protons in such a small place, even throwing in some neutrons in there, by even throwing in neutrons, you spread them out too much, and the strong nuclear force is no longer holding them together. So too many neutrons, too far apart, no strong nuclear force. Too little neutrons, they're too close together, and the strong nuclear force can't hold them together anymore. So they become unstable. And there's a point here at the 20 here, you'd have to keep on increasing the number of neutrons in there to hold it together, to hold it together, to hold it together. Eventually it just gets to a point where no matter how many neutrons I can throw in there, I'm never going to get a stable element because now the protons are too far apart. They will repel each other, and the strong nuclear force can't hold them together because, remember, the strong nuclear force only acts in a really small distance. So at the very top here, you can see everything up past a certain point is just purely radioactive. You got half-lives over here. This is how long they actually stay or go for. Like the red stuff here lasts for 10 to the 14 years. That's beyond the age of the universe so far. Black is completely stable. And then down here is just really, really small. They create and they just disappear. So you can see it has a nice little trend, equal amounts for a while, and then it just diverges and goes crazy where you need more and more neutrons to keep it stable because this protons are trying to force them together. We need more of that binding energy, and we need more space between the protons to allow the nuclear force to hold them together. Okay. But if they're unstable, they're going to break down. They always want to go to be stable. So these unstable stuff will undergo what we call radioactivity, radiation to become more stable. So it's going to kind of restructure itself by spitting out particles. And we're going to talk about that in the next lesson. And I'll see you then. Bye.